Hello and welcome back again. This is next part of this intro coding series that I've started, and I promised that we will start looking at some actual code this time, or to actually do some code. However, I've noted down some things that I'd like to fix and to streamline the code a little bit. So the first thing that I want to do is for this part here. This is, as we mentioned in the last episode, setting the screen memory and the graphics memory for the VIC chip for where to fetch the character set and where to put the screen memory. However, it's I do have a small little snippet to make this a little bit smoother that I mentioned last time. So I will find this and show you how this works. Let's see, there we go. So it's called set graphics bank. It's a sudo command. So it's basically set the graphics bank to bitmap memory and screen memory. And it sets the D018 by taking the screen memory value, and then he ANDs it with this value, which means he keeps these 4 bits and the rest he discards. And then he shifts it to the right 6 times. So it goes 1, 2, 3, 4, 5, 6, and then that is the setting that he will use. And then secondly, this is for the screen memory, and then it's for the bitmap memory or the character set memory. He will fetch the value and he will AND the same bits, and he's gonna shift it 10 times from the bitmap memory, and then he ORs these 2 values together. That will create the correct value for D018. So instead of knowing that I have to use 18 for 0400 and the graphics memory from 2000, I can just pass the actual addresses and he will calculate via this sudo command what the value is. Additionally, DD00, that is actually allowing you to switch the graphics bank as well. The VIC chip can only address 16 kilobytes, and in order to access all 64 kilobytes that is available in the memory, we need to bank switch between them also, and that's done with this DD00. So he will fetch and this DD00 does other things as well. So this is set up to be handled safely. So he will keep the 6 most highest bits, and he will clear the 2 lower bits. And the 2 lower bits, those 2 will give any combination between 0, 1, 2, and 3, which is the 4 different banks. And he will then URA in the value from 3, because you have to invert it to get it right. It's not 0, 1, 2, and 3, which is actually bank 0, 1, 2, 3. It's like opposite. And then it's the screen memory, which is right shifted 14 times. And then you can write that and get the correct bank selected based on the screen memory. So that's it. So in order to use this, colon set graphics bank, and then 2000 and 0400. Now that should work if I comment out that one. So let's just test it. we need to have a separation here. There we go, and that looks fine. Now, since I have defined this higher up, here I have the logo char upper. I fixed some of the typos, by the way, in between the episodes here, but that's the only thing that I did. So I paste that in there, and then I will also paste in the screen memory, which is here. And there we go, done. So hopefully that works. So there we go. A little bit tidying up of the code here. Now I can just copy this one, and then here it will be the lower. And we're still in business, so that's fine. We no neither need to rely on this values. You can find overviews over these values and type them in directly. You can find them at least on Codebase. There should be a pretty overview over it. You can take a look at it if you want. Just so I have shown it to you. So here's Codebase. Address is up here, so it should be familiar. And is it under here? Maybe not. Memory configuration, here we go. And VIC memory organizing. Yeah, here we go, VIC banks. So here is the DD00 values for the different banks and where they are located in memory. And here is also how to do the code I just showed you in the snippet. And here we go, character memory and screen memory, and which values these 3 bits then defines the D018. And of course this is from 00 to 3FFF, and that is one bank. So here is one bank, and it's the same size for each bank. So you will take this value to select the character memory, and then the screen memory is then selected by these 4 bits. So that's it, just figured I'd show you, so you can find an overview over that here. Alright, so that's done, we also can make it on the last one here. And in this case, that should be fine. 1000 is the ROM location for the character sets. The VIC will always see that, actually. It's just how it works. Okay. That was that. Also, the setup that is made here for the IRQs and these things. This one we're done with, so that's fine. I also have made some standardized snippets for setting up these IRQs, and here's the initialization one, which is also a Sudo command I used for that. So raster-rq initialization, and you can pass the IRQ vector the raster compare value, and NMI vector if it is something that you want. If there is no NMI vector which is passed, he will do something which is called ground the NMI. NMI is non-maskable interrupt. It means that the IRQ flag will not affect it. So if an NMI happens, it happens. It will interrupt whatever is going on. And this is one way to handle it. So basically this just fires off NMI and it never acknowledges it. So that will keep the line low, and you have to reset it in order for it to re-trigger. So you just keep it here. Or you can also set up an actual vector, and this NMI vector is the FFFA and FFFB address locations. So that's that. The first part here, that's setting interrupt flag, disabling the CIAs, then it's setting up the IRQ vector. And then here is the raster compare value, which is then setting up the D012 and also the D011, which will set this high bit, which is basically that one. And this is a safe way to do that. ACK and enable and allow IRQs. So basically the code here, I could take that out and then I'm just going to copy this. And the first thing that needs to be passed is the IRQ vector, which is, as we know, IRQ1. And the next thing is the raster compare value, which we know is 32. Now, if I wanted it to be on a line higher than, let's say, 255, I would just put line 280 and it will figure that out. So string 32, and if I'm not mistaken, we can just leave that blank and ground it. That means the restore button is not gonna work, for example, run stop restore. The restore is hardwired into the NMI line, by the way. So let's see if that works. Yes, it does. And let's take a look in the memory, and here's the new code that is generated now. Also taking care of NMI, and here we see it's 32 to D12, and then he keeps the high bit to 0, and then we are sure it happens where it should be. So that's good. That worked fine. That means that we don't need this anymore, because this is already handled. Now I like to call this asynchronous, which means it's not synced with anything. It's the code that runs when nothing else runs. So if I later want to make things happen that is not strictly relying on the raster, I can just put that in here. All right, so this one is good. Now I'd also have something which is called a lead in and lead out. For the lead in part, this is another snippet, and this one has the option to actually stabilize the raster as well. So it has a built-in stabilization routine. Now the first thing that happens here, he pushes the registers onto the stack, and yeah, first the A, and then it transfers the X to the A and pushes the A, and the Y to the A, and it pushes the A. So A, X, and Y is pushed onto the stack in that order. Then if we also tell him to stabilize, okay, we can go through this code just quickly. He sets up a wedge IRQ to the IRQ vector. Increase D012, that means I want a new interrupt happening on the next line. I will acknowledge the one that I'm in. I will transfer the stack state to the X register. I will allow interrupts to happen, and then I will just keep on with the no operation. And then sometime during this execution of these NOP commands, a new IRQ will happen due to the amount of timing that is spent from the IRQ happens until he pushes and does all this stuff. So there will happen something here, unless it's 65 cycles. You can add another NOP here. And then the first thing is to restore the stack pointer, because this will mess it up. And then do some timing, which is basically if it's a PAL, it's this timing. If it's 64 or 65 NTSC, it's that timing. And then it's basically to check the D012. Then the timing will, we know exactly, it's either 0 or 1 displacement in timing due to the NOP is a 2-cycle command. So it means we know that it can maximum be a jitter of 1 cycle for when this happens. And then we know exactly how much time has passed until this instruction here is. He will check the D012 and he will compare D012 with itself. And then the 0 flag, if it's equal, it's on the same line. If it's not equal, it's on the next line. So that is the 1 cycle that will tell you if you're on this line or if you're on the next line. Your jitter is 0 or 1. And then based on that, if it's equal to, and the BQ command, the branch if equal to command, if it's not taken, it is a 2-cycle command, and if it is taken, it's a 3-cycle command. So basically this will take either 2 or 3 cycles to happen based on if this compare was true or not. And it's quite genius, and then you will have actually stabilized it. So from that point on, you know exactly where the raster is down to the cycle. So, but for this code for now, I don't need it. So I just actually need this part here. And to do that, I will just take this part. And I'll just put that here. I could just put a 1 here and then it will add the stabilization. But for now, I'll keep that. So that is the lead-in. So basically, without the stabilization, it just pushes the registers, and that's it. So that's quite straightforward. Now, I mentioned last episode that we don't need to do that, and that's true unless I start adding some code in this asynchronous part here. Then you have to do it. So it doesn't really matter now, but I might as well set it up. And then I have on the same way is the IRQ lead out. And basically here it is the IRQ vector to the next IRQ. And again, a raster compare value. So he set up D012 and D011. And he sets up the IRQ vector and he acknowledges and he restores the registers and the exit. So this part here, let's see. The next one should be IRQ2 at that location. Now that means that I don't need to do that one. 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 And I don't need to do that one. I think. So let's see if that works. No, it did not. It looks to be in... Yes. Because this one will preserve the D011 value. And since we want to actually change it into back into character mode and not bitmap mode, we will need that one. So let's see how that works. Yes, there we go. So we'll need this one to switch it back to character mode. So we don't need that. So there we go. It's a little bit shrunk down. And then for IRQ2, we have the raster IRQ lead in. It will be the same. And it will be the lead out. And this time it will be IRQ3 and it will be line 12. So the delay, maybe we need to adjust it. This one is fine. We can delete this there. So done. So let's try that. See if the timing is still good. It looks okay. Just for the fun of it, if I were to turn off this timing, just to show you what it will look like then. Well, yeah, there you can see there's some bug here. There. So this will push that bug out on the side, so hide it in the border so you cannot see it. So that is good. Then let's do IRQ3. Could be that we don't need as much as 8, maybe 7 will be fine. It's not a big deal, we can fix that later. And here we want to keep this one because that will tell it to set the bitmap mode. And it's single color, that's fine. And then it's this one we don't need here. But let's just copy that. Make sure we got all the information. So this will go back to IRQ1. We'll be back to 32. We don't need these ones. We don't need that one. And we don't need that one. Yes, there we go. So now we've baked this into some Sudo commands to tidy up the code, or maybe it makes it more complicated, who knows. But for me, this is easier to follow. So another thing here, you notice this decrease D020 here and there, and then it's increasing them both here. Basically what's happening is that at this point, when we are at this point on the screen, when the raster hits and is at exactly this point, it changes the color on the screen, and that is actually the color that you see on the side here. It is black, and then here at this point it changes color to light gray, which is 0F. It goes from 0, which is black, and decrease with 1, it goes to F. It's the light gray one. And then he will, for as long as the subroutine logo xmove is running, he will keep that color. And then he reaches this point, where he has the text routine coming up, and then he decreases the color once again, which then is 0E, which you remember is the same light blue color you see up there. And then when that's done, he puts the 020 back to 00. So this allows me to see that when the raster starts up here, it's drawing every line, and when it comes to this point, he starts to calculate and move all the logo stuff. Now, I mentioned the last time, if this here was actually happening up here, so that means that you are drawing it while you're updating it, you're gonna get a lot of tearing and bugs. So you need to separate. If I want to do something down here, I can put the routine to do it up here, which will allow me to run things at full frame. So that's that. Right, so let's see. What else did I have on my list here? That was the graphics bank and the IRQ. What I could do is yeah, it's not critical, but I could define the location where these splits are as well, based on the size of the logo and these things that is defined up here. But you know, it's extra work for not much gain. If I need it later, I can do that. Okay, that was done. Now another thing that I felt I did not explain very well. Here, this is our test code. So what I'm gonna do is I'm gonna steal this. I don't need the library, I need the move command. So I'm just gonna borrow these ones. So move 16 from main to 1000. There we go. Now this doesn't do anything, but I just wanted to show you the code output that comes from this. So it compiles to 080. Okay. So this is the actual output code, and down to here we are okay. Now here, if you notice these 4 lines here, that is actually the move command, and then you see that main here, that is the label main, which is before the LDA 00, and that's up here, and that's at memory address 080E here. So he will fetch the absolute value 080E and put it to 1000, and then the absolute for the next, which is that one, which is F, and he will put that to 1001. But if, as I say, I actually want to keep the actual vector value instead, I just put a hash in front of this one. Oh, this monitor pops up on 3 windows on the other side there. So D083, and now you can see that it actually fetches the value 0E and 08 and put them to 1000 and 1001. So that's the difference on that one. I just wanted to show you how that works. So okay, another thing that I just briefly wanted to show you was this part here, and this we have a memory location, X Movo logo stuff, and the actual loops here. What does the code look like when it's generated? So let's take a look at that. And to actually find it, let's see, X move logo stuff, that's, oh my lord, that was small. 096A, so D096A. Here we go. So here is what is actually being exported from this loop code. A lot of lines with LDA, STA, LDA, STA. So instead of writing, and of course this is for all the lines of the logo. So there's one of these for each line of the logo. But it's more compact, my way of writing it. So figured I'd just show you that as well. And then last but not least for the code thing, you might have noticed that the original logo had or was in grayscale or gray colors, and the logo here is of course blue. There is nothing that stops us from putting in this to other colors. So for example, this one here we know is the 03 is the lightest color, so I can put this to 01, which is white, which is the lightest color there is. And this is the medium color, so I can put that to, yeah, 08, light brown. And then this one here I can put to D, which is actually dark green, should be. So now it should be a greenish brown logo. And there we go, green and brown. So that's how you control these colors. Now, if I were to put this one to 5, which is the actual green color, it will be in single color, all green. So I have to add 8 to that value, as I mentioned last time. I probably should have demonstrated that. So anyway, let's put that one to E. This is the middle color, so let's put that to 4. That one to A. That should look really ugly. Yeah, so different color scheme. So you can mess around with this as much as you want. So anyway, if I want it in gray, I can put it as possibly as gray as we can get it. Now there is a problem. I cannot get the darkest gray because all the gray colors are colors that has a higher value than 7. So 0 to 7 is the only colors that can be. So then I would have to change around the attribute. So this would actually have to be the white color, and then the two other will be the gray colors. But it's not very important. So for now, I'll just leave it like that. 1 was a bit brutal, though. Maybe 7. Yellow. Still a bit brutal. F. There, that's gray. So a little bit gray and blue. All right, so that was the colors. And then the last thing I just wanted to mention, this has nothing to do with code or anything, but I will not add any SID music to this for obvious reasons. Now I can't even make 2 notes on any musical instrument in the planet that we live on, so that's not going to happen. So what I'm going to do is I will overlay some of this free music that is part of YouTube and put on top with this intro. That doesn't mean to say that I'm not going to acquire some SID music later, which maybe somebody can make up for it. But for now, that's how I'm gonna do it. But the SID is, yeah, very cool chip on the C64, very iconic. So there's one more thing that I would like to do, and this function and this Sudo Commands, I don't want to keep them here in this code. I want to add them into my library. And to be very honest, that's not very difficult. So I'll make a new text document here. I'll call it MOV16 ASM. And then then I have a file here called Sudo Commands. And I'll add it into this list. Actually, they are capital letter, so we'll keep it like that. That's one thing I started on. I'll delete that. We don't need that. So what I'll basically do is I'll just cut this out from here, add it into its own little file, save it. It's included here, and it should still work, and it does. All right, and then we'll do the ink 16. Ink 16, save that. Don't need that anymore, don't need that anymore. We'll just put this into here, save it, run it, and still good. And then it's the function. That should be a different place here. So also here is RGB. Actually, that I didn't show you, but I'll finish this first and then I'll show you that one. So yeah, that's actually not what I was doing, but I can put it there, then I'll remember. So I'll cut this one out from here. Paste it in there, save that, and add it to the function list. What was the file name again? Save, done, and run, and we're good. So that's added to the library. Yeah, done, and off with you. So the RGB function, if you remember last time, we have this set palette RGB. That is actually a function. I didn't show you that, but and this is a function set palette and with RGB values, which is a structure which I have made, which is called RGB. And then he fetches the R component, which is then the red value, multiplies it with 65,536. It takes the green, multiply with 256, and it takes the blue, and he adds them together, and he returns that. So that's how you get RGB colors based on this setup. And the reason I did it like that is because it's if you remember how I actually read out the RGB colors from the Paint program. So that's why that was done like that. But anyway, we have shrunk down our code a little bit, gotten rid of some things we don't need. That's good. Now, I don't want to make this too long an episode, so this was just a little cleanup and things. And the next part now is to start producing some graphics from this routine. And it's I have pre-made some tables that will point to the location of each 3x3 memory block. So, and the table is 96 bytes long because it's 96 characters, and this is the low byte and this is the high byte, and this is the char set location, which is the character set for the 3x3 char set. And then he adds I multiplied with 72, which is basically 72. That is 3x3 by 8. 3x3 is 9. 9 by 8 is 72. So every block of 3x3 block of characters is 72 bytes large. And that is located here, 4000 to 5AFF. So I can take a quick look at it, what this actually means. Oops, that was big. They changed the key bindings to this, and it's confusing me as hell. So we call this char set vector low. Char set vector low is at 0C2A, so M0C2A, C2A. Here we go. So starts at 00, and then it's 48, which 48 should be 72 hexadecimal. And here is the other value, so 4000 here, 4048, 4090, 4000D8, and then it goes to 4120, so it wraps up to the next one and keeps up going to 5A B8 there, 5A B8, 5AFF. So it's got a little bit garbage on the end due to some of the larger characters, so that sounds about right. So this table means that I don't have to calculate. So when I read a value or a letter, I don't really have to need to multiply it with 72. I could do it real time, but there's basically no point to do it. I just take the value of the character and I look up the low and the high vector, and I will know exactly where to fetch the graphics data. So just to let's say we have A, then I will fetch the low byte with the index X and the high byte index X. And I have some zero page defaulting, so it's a long time since I used them, so I don't remember what they are. Let's see. So set P register, okay. Set P register 1 low. High. There we go. It was low and high. Yes, low and high. Good. So now I've made a pointer to the location of where the A is, if I remember correctly. Can we do this? There is a function to, let's just see if that works. Yes, it does. But anyway, not very important for this exercise. So, the next thing we need to know is where to actually write this. So I will just set that up manually. for this case. So I will write it to, say, 3000. Now I'm going to use indirect addressing here for this case. I'll see if that's how I'm going to end up doing it in the end, but at least for the fetched values, I think that's going to be how I do it. Now, so this will be set p register 1. This will be register 2. Yes. So 8 bytes, just to copy that brutally, just to see what, or to show you how this is going to work. And another thing I have to do is to actually change the graphic bank to 2000, because one bitmap screen is located from 2000 to 4000. There we go. Now 3000, that is the location for it, and that was a little bit wrong, so we'll see if we can move it a little bit. So let's put it to 40. That's not showing at all. Ah, crap. Sorry. There. There. We are starting on the left side here. And this is actually the upper part of an A, should be. Now, from the layout, we can see that the first value is here, and the second value is going to be output on the side of it. So that means that I can actually continue outputting, and I should get the second part of the A, and there we go. Now the A from the width table is only 2 characters long, so there's going to be no point to write the third one because it's going to be blank. So at this point what I need to do is I need to change, and this is going to be some manual operation. I might make some individual routines that are tailored for the various width characters. I have one for 1 character wide, one for 2, one for 3, and one for 4, etc. It might be that's going to be the way I do it. I haven't quite decided yet. But anyway, this outputs the top part of the A, and if I wanted to output the next part below it here now, I would have to change the I can still use the index register. So I'll skip the 8 next bytes because I know they're blank, and that should allow me to fetch the next part of the A, but I cannot write it to the same location because that is going to be to the right of it again. I need it below, so I actually have to add a lot more to get to this position on that side. So I might make some tables for this also, but this is just to show you I wasn't actually planning on going this far this time, but just to get some coding done and see how show you how this works. Just to demonstrate what happens, you will see that well, it's not showing anything because it's probably just blank, but I mean there is no graphics there. There we go. So now he adds 8, so he will actually write to this part, and doesn't quite seem right either, to be totally honest. Yeah, looks like a lower part or something. So this might not have been totally. Well, it should work though. All right, well, we'll pick this up next time, and we'll find out. But as I said, it's when writing to bitmap, and we're going to write to 3 different lines, we're going to have to probably use some tables to put us on the correct line instead of using indexing like that. So once I've finished, this is obviously not the way to do it. When I'm done drawing up the 2 or 3 or 1, or depending on the width, I need to change these vectors at this point so that it's actually fetching the correct data and outputting it at the correct location. And then comes also the horizontal shift and alignment of it. So it's a little bit some things that needs to be put into place. But okay, that's it. I'll leave it here for this time, a little bit shorter this time, and then we'll pick back up at the next opportunity. So take care and keep up the happy coding, guys. Cheers.